Ladies and gentlemen, thank you for being on our program. Today's guest, well, what can we say about him other than his work on the James Webb Space Telescope? It's in the news everywhere, worldwide. We're looking at the brand new pictures, but it's more than just pictures. We have a new way of studying the universe, understanding birth and death of planets, of stars, and all in all, our lives. We are all stardust. And to be able to peer out and see billions of years of history, space history, because of this new instrument that we have in our lifetime, it's a very special time. It's a very special time even for me. I followed the space program for years. And one individual that had a very direct participation as part of a team, but still on this very unique project, James Webb Space Telescope, is Alfonso V. Feria, Ph.D. from Jet Propulsion Laboratory. And he worked on the cryocooler segment of the satellite, i.e. the telescope. And we're going to get a little bit of technical information from him, what it is. But let's get to know Alfonso in his early years and how it built up to now to this wonderful episode, historical time for all humanity. Alfonso, thank you for being on the program.
Thank you for having me, Armando. Always a pleasure.
Okay. Let's start. Alfonso, little child, you were born. And where were you born? And what were you like? Because I'm sort of building up to the area. How did you end up becoming a mechanical engineer in Mexico and now working on this fantastic telescope?
So I was born and raised in Mexico City. My father was a medical doctor. My mom was just a housewife. She was actually a nurse before she got married. And then when she got married, she decided to become a housewife, which we're very grateful about that. She took care of all four of us. And we grew up in basically Mexico City. One of the emphasis from my parents was always college. You know, there was not an issue. The question was not, are you going to college when you grow older? The question was, where are you going to go to college? What are you going to study in college? So that set of mine, you know, was already planted when I was very, very young.
You know, we always think of being a medical doctor as a very prestigious position, but in many countries, being a doctor was just a little bit higher than probably being a car mechanic. It wasn't something that was very well paid or very well respected. Obviously, a lot of responsibility.
Yeah, I mean, it is well respected because, you know, they save lives and, you know, they care for the people. But yeah, especially like Mexico City, the health profession is controlled by the government for the most part, and so the doctors that work in the health system are basically government employees, you know, and they earned a government pay. Is not an outrageous pay, but we were middle class people, you know. My parents did good in budgeting whatever little money we had, and one of the emphasis for them was that the kids learn English. And as you know, in Mexico, public schools don't teach English until probably high school. And so we were enrolled in a private school, mostly because of the English language. And I told you a little anecdote because, you know, I hated English. I didn't want to go to school because of English. And at 4th grade in primary school, I told my parents, I want to get out of the school. I want to go to a public school. Of course, they said no. And the irony of it is that I'm the only one in my family that came to the States. You know, everybody else is still in Mexico. And here I am. The one that hated English is the one that has to speak English most.
And your work is in English all the time. So it's
right.
the irony of that. I'm assuming you must have been very good in math. I mean, I'm not going to assume it. You are good at math. I mean, you were talking about very high-end hypothetical math. And then the whole idea of being good in that. And then how did you end up picking up the mechanical engineering side?
So when I was young, I wanted to be an inventor. You know, I was one of those kids that would take things apart and try to put them back together. So I always was interested in that. My father was also a pretty good handyman. You know, he would fix anything around the house, even though he was a medical doctor. But yeah, I like math. I really enjoy, you know, working with math, and I was pretty disciplined about studying and everything. And I think that came from my parents. You know, my father was strict father, you know, and everything had to be done, you know, a certain way. He also incited in us the punctuality. You know, he would take us to school and we would be there half an hour before school started. And, you know, so now when people say, you know, you have to be here at a certain time, I'm there at that time. You know, that's, you know, something that has been engraved in me also.
We have that in
And
common. I'm also like that. When I first met my wife, she says, "Why are you here?" And I said, "You said 7."
right.
Yeah, but none of my boyfriends ever show up on time. I said, I always show up on time.
Right. So then from wanting to be an inventor, you know, I at some point when in high school, I wanted to be in industrial design, which basically takes care of designing, you know, common products for households and stuff like that. And then talking to one of my friends in high school, he introduced me to mechanical engineering. And I thought, well, you know what? I could be an inventor, you know, being a mechanical engineer. You know, I could do so much more being a mechanical engineer. So that's when I decided to enroll in mechanical engineering.
We have a question from one of the viewers, Kurt Hahn. He asked the question, he says, you know, how did you feel about the availability of classes, if there were any, in the mechanical engineering side, so that you could get your hands dirty and sort of figure things out?
Then when I was, I went to the National University of Mexico for my bachelor's and my master's degree. When I started in school over there, there was actually a common field between mechanical and electrical engineer. So actually my title reads Ingeniero Mecánico Electricista, mechanical electrical engineer. And then from there, at the last year, you would pick either a mechanical area, an electrical area, or an industrial engineering area. At that time, computer science had just started. So it was also a common thread with the mechanical engineering. So we, in Mexico, you have to have a very broad education rather than very specific. You know, so having the same common subject matters, you know, for mechanical, electrical, computer science, industrial engineering was very helpful, especially for me. You know, I'm a kind of guy that I like to cover many things, maybe not to a very much depth, but at least, you know, be very broad on my knowledge, and so that helped me a lot being educated there.
Okay, I'm not a mechanical engineer, but I do know, and I have lived around engineers my whole life, it is not an easy profession in terms of study. You go in from your bachelor's in science to your master's in science in 1 year?
I did my master's in about 1 year. Yeah. I was in a rush. I wanted to get out of school as soon as possible. And my PhD was 2 years.
How can you be wanting to get out of school by going so fast to the next level?
Right. And my PhD was also very fast, as you know.
Yeah. But still, it's not a subject matter. You just sort of look at a few pages and then move on. I mean, very intense.
Yeah, the program was a 5-year program at the University of Mexico. But taking additional subject matters, I finished it in 4 years for my bachelor's. And then right after I finished my bachelor's, I enrolled in my master's degree.
So bring me back a little bit. Your father was a doctor. Did your father say, "Mijo, I hope you become a doctor"?
No, as a matter of fact, at some point I wanted to be a doctor. One day he took me to an operating room to see one of the surgeries. I went there, I liked it, and I said, you know what? Maybe I want to be a doctor. And, he said, no, I don't want you to be a doctor. And, being my father, I said, okay, he doesn't want me to be a doctor. I'm going to be an engineer. And same happened with my sister. My sister at one point told my dad, I want to be a doctor. And my dad said, no, I don't want you to be a doctor. But my sister was more stubborn, and she enrolled in medical school. And my dad wasn't happy at the beginning. But then afterwards, he was so elated, that my sister went into medical profession.
Wonderful. That's a wonderful story. Okay, so obviously you're learning English. What is the connection between you living in Mexico City and coming to work in the United States?
When I was finishing my master's degree, like I said, I was ready to go into the work field. I actually applied for the Mexican Navy. They were going to start building ships in Mexico. Oh. So I applied for a job there. But one of my professors in Mexico had studied in Milwaukee at the University of Wisconsin. And he invited one of his professors. When the guy came down to Mexico to give some lectures, I was introduced to him along with my friend Juan Carlos, and he basically recruited us. He said, if you come to Milwaukee, I can offer you a Ph.D. with an internal internship, which means I was able to work in a company in Milwaukee at the same time that I was doing my studies. And like I said, I was pretty much done with studying, but the internal internship, that's really what interested me about coming to the States. So I worked during my PhD, I worked for a company called JI Case, which is now Case International. It's a tractor company. And I was helping with the design of the tractor cabins, doing analysis work. So it was a lot of fun, actually.
Now, I'm trying to make a connection here, but we're not talking about it quite yet. That antenna behind you does not look like any kind of construction equipment. So now I'm really having trouble to understand your background. But let me interject here. You went through school very quickly. You went through a very highly intense program. So I'm assuming you really couldn't do anything when you were a young person other than just being in school all the time and studying. So you really never had the chance, or did you ever have the chance to sort of work on things and try to get an understanding, getting your hands wet and dirty, trying to figure out the mechanical world?
Yeah, when I was in high school, during summer times, I worked as an accountant aide, where my uncle was working in a watch company. And so I worked there summers, with numbers. And of course, I enjoy numbers a lot. And I liked the work. But then when I was ready to start college in engineering, he actually introduced me to his mechanic. They hired me as an apprentice in the shop. They used to do race cars in there, and then from race cars they were just doing regular cars. But I started working there, and I worked there probably 2 summers, without pay. It was basically as really an apprentice. Until one of the mechanics there said, well, you know what, you're actually kind of good. If you want to earn some money, why don't you come to my house on weekends? I work out of my garage and you can help me. And so I started going weekends. So every weekend, mostly Saturdays, sometimes even Sundays, I would go there and I would work all day, as a car mechanic. And something that is funny, because when I used to tell people, oh, I'm studying at mechanical engineering, the first thing that people would say is, oh, you know how to fix cars. And the reality is, yeah, I know how to fix cars, but not because what I learned in school, but because what I actually do on the side job.
You know, you remind me just of a story right now. You put me together in your network with someone who's an engineer now at General Motors, Guadalupe Bañales. And her story, which I also recorded, was that she used to hang around her dad as he was repairing the cars. And he would sort of shush her away and says, Mija, you know, this is not for you. And she'd come back and she'd watch and she'd watch, and she just learned so much. She was watching her dad, and eventually she started working on car mechanics. And now she's, you know, helping build cars for General Motors.
Right, right. I know Lupe very well. So, hi, Lupe.
You've been a mentor to many of us as well, and I've learned so many things from that. So, but how did you go from case construction and caterpillars and other kinds of machinery? How did you make the jump from there to the Jet Propulsion Laboratory, where now you're working on obviously space programs?
Yeah. So basically, my training in engineering was mostly design and analysis of structures, basically. So when I work at Case, you know, I work on tractors, on the structures of tractors. So I did the analysis for that. After I finished my PhD, I got a job in a small company in Milwaukee called Cooper Power Systems now, doing power equipment analysis. So I would do the structural analysis for the enclosures of these power equipment. Later on, I started doing some thermal analysis, some magnetic analysis using a method called finite element analysis. And so because of that background, that's how I ended up at JPL, because they needed an analyst specifically to design this type of antennas. When I started at JPL 30 years ago in 1992, they were just designing and doing analysis of these 34-meter beam waveguide antennas for the deep space network. And so being that I have done all this analysis work, you know, I fit it perfectly in the area. You know, the jump into the spacecraft came later once I was already at JPL, you know, but I really started with these huge structures, you know, 34-meter antennas.
Now, when you point to that particular antenna, share with us a little bit more. Were you designing the antenna itself, the properties that we're seeing, or you're talking about the mechanism inside of it for receiving and sending out telemetry?
No, I was working on the mechanical structural side. So I was working on the, you know, the dish, on the base of the antenna that holds that dish. And, you know, these antennas are steerable. So I also work on the motors and the mechanisms and the wheels and the gears to move the antenna. The electronics and the RF portion, it was different groups, and it is different areas. You know, I'm not an electrical engineer, not a communications engineer.
Okay, you don't have to answer the following question. You can take the fifth. Have you ever lost one of these antennas because of the incorrect analysis?
No, we haven't. Actually, these antennas, you know, this design, it's like I said, I started it 30 years ago, and we're still building this type of antennas. You know, I just came back from Spain, being 3 years there. We built 2 more of these antennas. Right now, they're building a new one over in Goldstone, California, and the plan is to continue building additional ones to augment the.
Why are so many being built?
Well, you know, every day we have more spacecraft in space, and so we need to communicate with them. And so there's not enough, we call them apertures, not enough antennas to receive and send all the commands. And so we need more and more. And, you know, we support mostly outer space stuff, but, you know, they even talking about, you know, instead of creating a new network for when we go to the moon, you know, using the DSN, the Deep Space Network, you know, to support the man on the moon. So, you know, there's more and more taxing jobs on these antennas.
Aren't you know, this little sidebar here, but technical question, aren't they thinking of putting the antennas up in space instead of on the ground. This is really far-fetched information on my end, but is that the case?
Not that I know of. I think, I mean, the network for support the moon, it's going to be on ground. And
So that's the next big thing, even though we haven't even talked about the current projects of the space telescope, but we're talking already about going back to the moon and that other aspects as well.
And you know, these, especially like the ground networks, the near Earth networks, are really just good for stuff that is around Earth, you know, the satellites around the Earth. So our antennas are not good for near Earth. We're really good for deep space, you know. And so here comes James Webb. We're talking about James Webb, and James Webb is going to L2, you know, which is a point out in space beyond the moon. And so the near Earth network is not able to support. So now they're asking the deep space network to support the James Webb. And of course, you know, being this huge program, they demanded a lot of time, you know, and they demanded time when they needed it, you know, during their trajectory towards L2, during deployment, during commissioning, and all that. So that took a lot of the time that the antennas were being used for other missions. Now they had to realize that, oh, you know what, we don't have enough, you know, and the more stuff that we keep sending out, you know, we're gonna need more and more. So we're really building more and trying to keep up with demand.
Wow. And just for a quick point of information, they don't use the same model that they built before for these huge antennas. I'm assuming they always have to use new material, new systems, new kinds of ways of receiving information. So it's always not totally back to zero, but you can't use the last model for the new one because you're totally working with a whole new set of circumstances.
You'd be surprised, but the structure hasn't changed in 30 years.
Really?
The panels that we use, you know, the front that you see, they haven't changed. What changes is, for example, the servo mechanisms, you know, how you move the antenna, you know, try to make it as smooth as possible, because these antennas, as you can imagine, you know, if you're tracking a planet or a Mars rover in Mars, you know, they move very, very slow. So when you see the antenna, you think they're stationary, but in actuality, they're moving, they're tracking the planet.
They're going with the Earth rotation and the planet rotation, and they're constantly adjusting.
So those things have evolved, you know, the servo systems, the electronics, the receiver portion, but the mechanical, structural, you know, it's as good as 30 years old. Wow. As a matter of fact, this is as good that we're now working on what we call a hybrid antenna, which the center of it is going to be optical panels, basically mirrors, and the outer is going to be the RF panels for radio receiving. So the inner panels, which are mirrors, is for optical communication, which lasers.
Oh.
So, and of course, these panels are much heavier, the equipment is heavier, but you know, people have been doing analysis now and they find out that the structure is very robust, and we are going to be able to support the new hybrid antennas.
Okay.
So, you know,
I'm no expert, I'm not an engineer, but I did do my homework, and cryocooler is keeping something very, very cold, I mean, in general terms. And you've been working on antennas. How did you end up from antennas to cryocoolers?
So working at JPL, one of the advantages is that there's many areas of study and research and work. You know, we have the DSN, which are antennas, but one big portion of JPL, which actually is the most famous about, is the spacecraft. So for the glamour of the work, you know, a lot of people want to work on spacecraft, you know, especially the Mars spacecraft. So after a few years of working on DSN, I jumped into the spacecraft side, doing some research and development work on inflatable structures for radar application. So these are structures that can be collapsed before they are sent out into space. And then once they're in space, you can inflate them and then they become a structure. So that was my first attempt to go into the spacecraft side. Then I was called back to work back on DSN as a group supervisor of the antenna mechanical group. So I did that also for a few years, but then I wanted to go back to the spacecraft side. So I jumped into the spacecraft side doing, again, analysis work. I was doing analysis work for several missions, you know, the space interferometry mission. I was working on one of the instruments for Curiosity, the X-ray source. And so being involved with the instruments and also being involved with the integration of these instruments, working in the clean rooms and seeing how these instruments are put together and what it takes to put these instruments together. I was selected to work with Northrop Grumman, which was a contract from JPL to build these cryocoolers for the MIRI instrument in the James Webb Telescope. So because of my background, I went down and I spent a couple of years down Northrop Grumman in Redondo Beach, helping out with the fabrication, integration, and testing of the cryocooler.
You know, I have some viewers who have some very specific questions about that particular work, if you don't mind me referring to it. The idea of why does the telescope need to be so cold? Let me read the questions and see we'll go into this. Can you keep it cold for 20, 30 years or less or more? This is a question that when I received it from Adrian Sanchez, I really had to think about it. Do quantum mechanics play a part in the design of it? And what are your hopes for the satellite? I know it's a lot of questions, but any of them that you want to.
So just to understand a little bit, the James Webb Telescope has 4 main instruments. And one of the instruments was developed by the European Union, by the European Space Agency, which is the MIRI instrument, is the mid-infrared instrument. So some of the pictures that you've seen lately come from that instrument. It's a mid-range in the infrared band, which captures a lot more information than what Hubble was doing. Hubble is an optical telescope. And so we're going a little bit to the right, you know, on the optical band to the mid-infrared. And that's where MIRI is. Now, in order to filter some of the noise that is coming into the MIRI sensors, they have to be cooled to about 6 degrees Kelvin, you know, which is just 6 degrees above absolute zero. You know, so it's very, very, very cold. In order to achieve that, they have this cryocooler developed by Northrop Grumman, which has several stages of cooling. And first, you cool it down to like 100 Kelvin, then you go a little bit further down until you get to the 6 degrees Kelvin. The way you do that is through helium. You compress the helium, and because of physics, you know, it eliminates the heat and creates this cold environment. It's like you said, you know, it does go into the quantum mechanics. You know, it's the physics there at that point are a little bit different than just regular physics, just because how cold you are, you know, at 6 degrees K. You know, the atoms, you know, are moving very slow at that point. You know, almost stopping but still moving. So by using these compressors and these very fine holes inside these compressors, you know, you're squeezing the helium and you're extracting all the heat and making it very, very cold. You know, just kind of in layman's terms on how this thing works.
If that's layman's, I hate to see the technical side. Give me a headache.
But it's also a closed circuit. So you're recycling all this. So yeah, it can last 20, 30 years just because, you know, you're not wasting this material. If you don't have a leak, you know, which we did extensive testing, you know, trying to avoid any helium leakage, because if you lose your helium, you know, you lose your instrument. And so it's a closed circuit and it can last as long as it's possible.
This is a personal question based on the questions of Adrian Sanchez. And my question is, where do you test this stuff? How, is it possible to get things that cold here on Earth?
Well, what's generating the cold is a cryocooler. Right. So what you're testing is that cryocooler, you know, at the end, you put a little thermometer at the end and you see if it's actually cooling to that temperature. So yeah, you can test them here, you know, you put them in a little chamber and you do all your testing. But what's generating the cold is actually the cryocooler. So,
wow.
So, yeah.
I would think it's a special thermometer, not the regular one off the wall and just stick it in.
Right. Not your regular
think mine goes down to almost absolute zero. I don't think it goes that cold. So it's something really spectacular. Right. I applaud your work in this area. And unfortunately, we're getting close to the end of the show, but let me ask this question. When did you finally take a deep breath and feel comfortable and you realize what you have done? Because I mean, I can imagine that seeing this telescope still not working out there and for the first time opening up with all its complexity and you're thinking, oh my God, will my part work? And will it all work? When did you get that sensation like?
Well, it was not until I saw the pictures. You know, a couple of weeks before, I was invited. They were going to have a special event at JPL for the people that work on the program, and so I was fortunately to be invited to that event. You know, and I was really looking forward to seeing the pictures firsthand. Was a little bit disappointed, to tell you the truth, that they showed them to Biden first. At least one of them, but that's okay, you know, that was okay. But yeah, it was very, very, very satisfying, you know, looking at those pictures and, oh, you know, the resolution and the information in the pictures. And like they were saying at the presentation, you know, this is the Hubble telescope would take a week to several weeks to take one image. You know, the James Webb telescope pictures that we saw, they were taken in about a week or less than a week, you know, just a few days. So can you imagine what's coming? I mean, once they really start looking and processing all this information and focusing the telescope for more than just a few days into a certain area, I think we're gonna learn a lot, you know, and that's very satisfying.
I want to thank you for doing your part as well with all the teams of making me so thrilled that I'm alive at this era to see something so groundbreaking. I mean, I thought landing on the moon was out there, not that it's not at its time, that the shuttle and the programs and landing on Mars, and now this that opens up the whole universe to us. Thank you.
Sure.
Thanks to
and
all.
Just a tidbit of information, you know, how do you differentiate between a Hubble picture and a James Webb picture? When you look at the Hubble picture, the stars have like 4 beams of light coming out of them. When you see a James Webb,
like 3 points, 4 points,
like 4 points, yeah. But when you see a James Webb telescope picture, it has 6. And that's just because of that, you know, configuration of the hexagons and the telescope. So just look at those 2 pictures and you will see the difference.
That is very unique. Now we have very specialized information.
Right.
One more question that I have, and it's a great question, and Guadalupe Bañales shared it with us. And the question is, what is your advice to aspiring engineers?
Tenacity and always keep focused. If you have something in your mind that you want to do, just keep at it, insist on it, and study hard and keep at it. You will get there. I never in my wildest dream thought I was going to be working for JPL, for NASA, but it's so satisfying. So if the young kids, they have something in mind, they can do it, they can achieve it if they wanted to. Just they need to do it the right way.
Well, if I may add to your
Responsibility.
answer as well on my behalf, knowing I've known you more than 20 years, Alfonso, is you have a fantastic ability to work with many different kinds of people on many levels, many cultures. You have an exceptional way of getting along with people and putting teams together. I mean, you helped me put together a presentation for the Mars rover. You just keep bringing people together on all levels, and you have a real dynamic ability to do that. And I think that should be something that I know you don't take it for granted, but something I should point out to people, that you have it. And I think it's also been part of your one of many points of your success.
Thank you. I appreciate you. You've always been a big supporter, and I appreciate that.
Oh, anytime, anytime. Alfonso, let me close the show by putting it back on you. Anything you want to say, given all the reviews and all the information we're getting about the telescope, but also on a personal level, your closing statements, Alfonso.
I'm just very happy to be where I am. Getting up every day and being happy to go to work. It's something that not everybody can say, and I've been doing it for more than 30 years. I think the attitude that you have and that you bring to work is very important. And even if you're a dishwasher, or you're a professor at the university, just go in with a good attitude, and that will help. Overall, your life will get much better.
Ladies and gentlemen, we've been talking to a fantastic engineer, Alfonso Feria, at the Jet Propulsion Laboratory NASA. And he brings us his work and his appreciation for the work of the team to put together the James Webb Space Telescope. And it's just opening up our universe further and further and further. And the question that I'm going to ask Alfonso in the future show is, what's next? We're going back to the moon. We want to go back to Mars. But in the world of these telescopes and what we're going to learn and all the new information we have to process and data from the pictures we're getting, and we're going to going through philosophical questions as well as scientific ones, is just overwhelming. It's just amazing. And it's just the start. So again, I can't thank Alfonso for being on the program. And I'm just thrilled with all the new information that we have and that it happened in my lifetime. I can't say thanks enough to all of you for that, to NASA and JPL for you guys putting the stuff together. We want to thank 3 individuals for sending us question. Kurt Hahn, Dolores Guadalupe Bañales, and Adrian Sanchez. We thank them for their questions. Alfonso, éxito, success to you. Continue building these wonderful machines and let our imaginations fly with no limit.
All right. Thank you.